Hello, Algebra 1. Welcome to our Square Roots mini topic part 2, covering solving quadratics using square roots. So today you're going to see equations, quadratic equations like this. So this is your standard form, ax squared plus bx plus c equals 0, right? If you remember that. Well, you're going to see that the bx is not going to be there, right? There's going to be no bx. So because there's going to be no bx term, we need to solve this in a different way, right, than what we would do as we taught you in topic 9. So the first thing I want you to focus on is isolating the x squared. So we did something like this when we did the absolute values. We isolated the absolute value. Well, same thing here. We're going to isolate x squared. So in this case, you got to move the c over. You got to divide by the a to get x squared by itself. Once you have the x squared by itself, you're going to take the square root. So here's where our idea of using radicals and simplifying is going to help, right? So if I have x squared equals some number, I'm going to take the square root. What that's going to do is that's going to cancel my squared here and leave me with the x. Now, if you remember from solving quadratics in that whole topic 9, there are 3 options for answers. You could have no real solutions, 1 real solution, or 2 real solutions. We're going to focus on 2 real solutions because when you take a square root of a number, you get the positive of that answer and the negative of that answer. And that would be whatever the square root of this number comes out to be. So you get 2 solutions. So keep that in mind. When you take a square root, you should always put a plus or minus in front of the square root of the number on the other side. All right, so let's solve a couple of problems involving this. Okay, so now example 1, it says use the square root property to solve the equation. The equation has real number solutions, right? So I do not see this bz term, right? There's no z term, so no bz. So the first thing I want to do is I want to isolate the z squared. I want to get this by itself. First thing I'll do is I'll get rid of the minus 50 by adding it. I'm going to add 50 to both sides. So the 5z squared comes down, the 50s are gone, and 0 plus 50 is 50. And now again, I want to get the z squared by itself. This 5 is multiplying with the z squared, so I will divide by 5. When I divide by 5, z squared is here, and that equals 10. 50 divided by 5 is 10. And now my z squared is isolated, right? So now we need to take the square roots. When I take the square root, my z comes down. Over here, I'm going to put a plus or minus in front of this square root of 10. And now it's going to ask you to simplify it radically. So now you could type this in Desmos. I'm going to tell you it's not nice. So now we're going to come over here and we're going to break it down. Well, 10 is only 2 and 5. Those are both prime. Notice that neither of them repeat. So there's going to be nothing that comes out of this square root. So this is your final answer, plus or minus the square root of 10. Okay? Now, it might ask you to round to 2 decimals, right? So I'm going to plug this into Desmos and we're going to show. Okay, so if we do the square root of 10, and again, you don't do the plus or minus, you just put the square root of 10. And there we go, 3.16. The 2 leaves the 6 alone. So your answer could also be z equals plus or minus 3.16. And again, that means that this quadratic crosses the x-axis twice at positive 3.16 and negative 3.16. All right, next, let's take a look at the next problem we have here. Example 2. It says an isosceles right triangle has legs of equal length. If the hypotenuse is 10 centimeters long, find the length of each leg. So when I see right triangle, and I'm talking about the lengths of the sides, I immediately think of Pythagorean Theorem. Right? I told you we were going to use this Pythagorean Theorem a couple times. P-Y-T-H, Pythagorean Theorem. It is a squared plus b squared equals c squared, right? Now, this is an isosceles right triangle, which means that 2 of the sides are the same. So that's why this is x and x. They're equal, right? And then the third side is 10. So remember, the legs are the 2 sides that make the right angle. So this is the right angle. So those 2 sides are the legs A and B. And then the hypotenuse, right, which is typically the diagonal side, but it's always across from the right angle. So you see what I did here? I used the right angle box and I put an arrow line through it. That always points the hypotenuse. This is your C. All right, so here's A, here's B, here's C. So we're going to do x squared plus x squared equals 10 squared. Well, now we have like terms. So there's nothing to get rid of here. We just have to combine these like terms. This is a 1x squared and a 1x squared. 1x squared plus 1x squared is 2x squareds. So 2x squared equals, and we do square the 10, and 10 squared is 100. So now I do have to get the x squared by itself. This 2 is multiplying with the x squared, so I have to divide by 2. And I get x squared equals, and that's 50. So now I take the square root. That's going to cancel with the squared and leave you with the x. Over here, we're going to put the plus or minus, and we're going to put the square root of 50. Now, let's talk, though. This is a real-life problem. We're talking about a triangle here. We don't want the plus or minus. We just want the positive answer, so you don't need the plus or minus. And now, it's going to ask you to simplify and then possibly round the answer. So we're going to simplify first. So if we go with the square root of 50 in the calculator, it's not nice, right? So here's my 50. So I'm going to do 2 and 25. 2 is prime, 25 is not. But 25 is a perfect square, 5 and 5. So again, if you know your perfect squares, you might be able to jump ahead and get the answer, right? So this means that 50 is 2 times 5 times 5. That's 2 times 5 squared. Anything squared comes out. So this 5 comes out. The 5 squared's gone, but that 2 stays on the inside. And that is what the square root of 50 simplifies to, 5 square root of 2. So your length of x is 5 square root of 2, and it's in centimeters. And now we want the rounded answer. So now watch this, right? So square root of 50 and 5 square root of 2. If I go back to Desmos, and I type in what I just got, 5 square root of 2. All right, so there's my answer rounded, right? 7.07. The 1 leaves the 7 alone, so x is 7.07 centimeters. But now watch if I go back to the original problem, right, the square root of 50. You get the same answer. So remember that when we simplify radicals, we're not changing the value, we're just changing how it looks. We're making it look prettier, simpler. Okay? And there you go. All right, last but not least, example 3. Let's take a look. All right, so example 3 says, the base of a 12-foot ladder is 6 feet from a building. If the ladder reaches the flat roof, how tall is the building? So this is a typical geometry involving a ladder, right? So we have a building. All right, let's start with this building. Okay, and it's connected to the ground, right? And we have a ladder leaning up to the top of the flat roof. So here's my ladder, and my generic ladder is this. There's my ladder. Okay, so the ladder is 12 feet long. So this length is 12 feet. The base of the ladder, so this is the base of the ladder right here. So the base of the ladder is 6 feet from the building. So this length right there is 6 feet. And we wonder if the ladder reaches the flat roof, so there's the roof, how tall is the building? So what is this? Call that x. This is what we're looking for. Okay. We're going to assume that the ground and the building are perpendicular. Ooh, perpendicular. That means make a right angle. And now I hope you can see the right triangle. We're going to use Pythagorean Theorem again. Pythagorean Theorem, which is a squared leg squared plus b squared leg squared equals c squared hypotenuse squared. So again, the right angle is formed by the legs. So 6 is a, x is b, and then the right angle, I drew that arrow, is the hypotenuse c. Okay, so let's fill in what we know. So this is 6 squared plus x squared equals 12 squared. Now notice this time the 6 squared and the 12 squared are on opposite sides. So we're going to square them individually. So just type in 6 squared in the calculator, you get 36. The plus x squared just comes down. Types 12 squared in the calculator, it's 144. And now we have to get the x squared by itself. There's this positive 36 right here, so get rid of it by subtracting. So x squared equals, and we do this, it's 108. And now we need to take the square roots. Again, we only want the positive answer because this is a real life problem. So x equals the square root, the positive square root of 108. If we type that in the calculator, it's not going to come out nice. So we're going to break it down radically here. So I know that 2 goes into 108. 108 divided by 2 is 54. 2 is prime, 54 is not. I know that 2 goes into 54 27 times. Use division. 2 is prime, 27 is not. 2 does not go into 27, but 3 does. 3 goes into 27 9 times. 3 is prime, 9 is not. And 9 is 3 and 3. Okay, So now the square root of 108 is the square root of 2 times 2 times 3 times 3 times 3. Group them by 2's, so I have 2 2's, and I have 2 3's, and then a third 3 by itself. So I have a 2 squared, a 3 squared, and a 3. Anything squared comes out because of this hidden index of 2. So this 2 comes out, it's gone. This 3 comes out, it's gone. And what's left inside is that 3. 2 times 3 is 6, and then the square root of 3 is left inside. So the value of x, the height of this building, is 6 square root of 3 feet. Now in real life that means very little to us. So go ahead into Desmos and let's type it away. So in Desmos we're going to do 6 times the square root of 3. And I'll round to 2 decimal places. So that's 0.39. The 2 leaves the 9 alone. So our height is 2.39 feet. And there you go. Another great example of application of Pythagorean theorem. All right, thanks for watching. Good luck on the practice.